regarded for his foundation research in quantum information theory, open quantum systems, quantum thermodynamics, and quantum optics. And in addition, Professor Ghosh will also deliver a special colloquium titled Quantum Batteries, Science Fiction or Reality, which I will unfortunately miss, but I will try to join through YouTube, exploring an exciting and rapidly developing frontier of quantum thermodynamics. So I would like to also express my sincere gratitude to our director who has extended generous support to organizing this program, and to all the speakers for their willingness to contribute to this program. I would also like to thank Varini and Mani who are sitting outside, you have actually seen them, and all other administrative and technical staff and everyone who will be involved and has been involved in organization of this event. Most importantly, I thank all of you for all your enthusiasm and interest and in joining us for this week-long program. Theoretical physics has always advanced through a careful balance between mastering and establishing ideas and questioning their limitations. It is our hope that this series will not only strengthen your understanding of the fundamentals, but also give you a glimpse of how these ideas continue to shape modern research. Perhaps some of you, I hope, it may even be a mark, this might even be a mark for the beginning of a future career in theoretical physics. So I hope this coming week be intellectually stimulating for all of you and enjoyable and inspiring to all of you. With that, let's begin the first lecture series. It's now my pleasure to invite Professor Subhashish Ghosh to deliver his first lecture. Thank you.
Okay, am I audible?
Yes, sir.
Okay, good morning. So what I am going to talk about is quantum information theory, so of course it requires a bit of quantum mechanics, knowledge of quantum mechanics also, but quantum mechanics basics will be introduced later. But now today I am going to talk about classical information theory, basics of classical information theory, and for that you don't need to know quantum mechanics. Okay, so information, I think all of you know, because you read books, you look at some documentary, you look at the internet, so everywhere there is some information. Now the question is that how will you quantify information? That is the first question. And secondly, which one you would like to call as information, which one you would like to call as data? Okay. So for example, there are plenty of organizations who collect data, right? Personal data, or something some organization which does this market survey, they take data from the market and all that. But the issue is that this data, of course, it has some information, but is it true that all of those data are useful. So what we need to figure out is which information is useful, which information is not useful, and we will have to quantify that. So let me give you two examples and try to tell you that which one is useful and which one is not, and this example will also help us to quantify the amount of information. So as I said, I will talk about classical information today, and from next class onwards I will talk about quantum information. So let me consider these following statements. Please tell me from the back, can you see this writing? Sun will rise on the east. Okay, this is statement number 1. Statement number 2 is it will rain tonight in Chennai. Okay, I hope all of you can read these statements, right? Okay, so if I look at these two statements, so first one has some information, second one has also information, but let's see. Sun will rise on the east. Okay, so this statement, does it contain any useful information? What is your idea? No information? No useful information. Why? It's a fact. So this happens every day. So it does not add anything to our knowledge. Okay? So this is a certain phenomenon, right? The first one, sun will always rise on the east. Okay? So this is a certain phenomenon. So this has no useful information, right? Look at this. Does it have, the second one, does it have any useful information? Why? Sorry, what? I couldn't hear. Can you? You can plan, of course. Of course. This is useful because, you know, in Chennai you don't get to see rain every day, every night, right? So therefore, this contains useful information. Whether tonight it will rain or not, that I don't know, but just, so this contains some useful information. Okay? So the question is that, so this is no information and this useful information. Okay? So now the question is how to quantify useful information. So for example, if I look at here, if I look at the rainfall in the night for the city of Chennai, then I may have, generally I will have some statistics that what is the probability that it will rain tonight in Chennai. Right? This is how the weather department works. So we will have some possibility of having rain tonight in Chennai, right? Okay. So if I look at the data, the statistics, I can figure out approximately that what is the probability of having rain tonight in Chennai. Okay. Right. Let me take this. So maybe if I look at the statistics, maybe you can say yes. Sorry, what? Yes. Yeah, because it happens every day. Okay.
If my query itself is the fact that where does the sun rise from, then the first statement also.
Yes. So because it happens every day, so it does not provide any useful information. What is useful information? Useful information means there should be some amount of uncertainty. Okay. So maybe if I look at the statistics, the probability of having rain tonight, maybe it's 1%, I don't know, 1% or even maybe less than that. Okay. So let us take another statement. Like 2/3 of Earth's surface is water, let's say. Okay. So is water, let's say. Okay. So does it have any useful information? Yes or no? Sorry? Again it is a fact. Okay, good. So yeah, so this fact generally does not change, it may change little bit but does not change, okay, generally. But I consider this for a different reason. So if I look at the fraction of area of Earth's surface, 2/3 of it is land, is water, and 1/3 of it should be land, right? Okay. So here probability of land or water surface, okay, this is what? This is 2/3, right? And probability of land surface, this is 1/3, right? Approximately, it can vary a little bit. Okay. So probability, I hope you know, right? What is probability? I'll come back to it in details. So this sentence basically it provides me these two probabilities. Okay. Now let us consider another statement. So let me erase this. Let's say, let me consider this statement, right? 2/3 of dogs in Chennai are street dogs. Okay? Yes.
Sir, the statement that 2/3 of Earth's surface is covered by water, isn't that a certain statement? Why is it probability?
Yes, all this is a fraction because probability is basically a kind of fraction. Okay, so this is, you can say that, if I choose arbitrarily some area of Earth's surface, okay, that may be water area, that may be land area. What is the probability that it will be a land?
Okay.
So that will be 2/3, right? In that sense, this is probability. So let us take this thing. 2/3 of dogs of the dogs in Chennai are street dogs. It may not be correct statement, but let's say, okay. So then remaining 1/3 are domestic dogs, right? Household dogs you can call them, right? So here again the same statement, that if I select a dog in Chennai, the probability that it is a street dog is 2/3 and probability that it is a domestic dog is 1/3, right? So therefore, probability that it is a street dog, this is 2/3, and probability that it is domestic dog is 1/3, right? Okay. So in terms of probabilities, if I look at this statement, statement number 4 and statement number 3, is there any difference? Don't look at now at these statements, just look at this probability, structure of the probabilities. Is there a difference? No, they are same, okay. So when we talk about information theory, quantification of information, it is these probabilities that will matter and nothing else will matter. Is that correct? Is that clear? So from now onwards, of course, which probability corresponds to which event, etc., that will matter, but the structure, that means the mathematical form of the probability or the values of the probabilities, that will matter in quantification of information, okay. So it doesn't matter whether we talk about dogs in Chennai, it doesn't matter whether we talk about earth surface, it doesn't matter whether we talk about, you know, the rainfall tonight in Chennai. What matters when we consider quantification of information is this probability structure. Okay. So what is information? If I want to quantify information, what is it? Basically, I can quantify information from two directions. One is that I have how much ignorance I have about some phenomena, about some data, about information, how much ignorance I have. If I can quantify that ignorance, that will be our quantification of information. On the other hand, I can also say that how much knowledge I have about some phenomena, some data, some information, that is also quantification of information, okay. So I can approach from both the sides. What we will do here, we will take the first method, that quantification of information is through your ignorance, okay. Both are same, it doesn't matter. So I will consider quantification of information as the quantification of my ignorance about that event, okay, about that information, right? Okay, good. And historically this is what people have taken. It doesn't matter, you can start from both these, any one of these sides, right? Yes. Exactly. So if you say from the perspective of knowledge, useful information means you don't have the full knowledge. So the first statement that I have written, that sun will rise in the east, do you have any ignorance about that event? No. So therefore the information content should be 0, because your ignorance is 0 there, okay, right? And let us make another statement, that sun will rise on the west, okay. If I make such a statement, do we have any ignorance about this statement? What ignorance I have? 100% ignorance? No. this is a false statement. Okay, this will never happen. So the probability of occurrence of rising of sun in the west is 0, right? So you can say that ignorance about this event, that sun will rise on the west, is 0, because I know that this will never happen. So what I want to say is that the information content of certain event is 0, information content of impossible event is also 0, right? Because for both the cases you have no uncertainty, you have no ignorance, right? Is it clear? Okay. Now let us look at, for example, this statement or this statement. Let us say I have this statement, 2/3 of Earth's surface is water. So of course, if I choose a portion of Earth's surface anywhere you want, it will not be land with certainty, neither it will be water with certainty, right? So what we have, only these probabilities, that this portion of land, portion of Earth's surface will be land, is with probability 1/3, and the same portion of Earth's surface will be water, is with probability 2/3. Okay? So do we have some ignorance about this statement? So ignorance in this sense, that I provide you a portion of Earth's surface. Can you tell me, without doing any experiment, anything, without looking into it actually, can you tell me whether it is land or water? Can you tell it with certainty? No. So you have basically ignorance about this fact, right, about this event. You have ignorance. So question is that how to quantify that ignorance. I said for certain event amount of ignorance is 0, for impossible event amount of ignorance is 0. Okay? So therefore their information contents are also 0, because you don't have any ignorance. But for this kind of events you have some ignorance which is neither 0 nor 1. So the point is that if I look at some event, like it will rain tonight in Chennai, whether it will rain or not. If I look at some event, then my ignorance will be higher if the probability of occurrence of that event is lower. Do you agree with me? If I look at some event, the information content of that event, right, or you can say the amount of ignorance about that event will be higher if the probability of occurrence of that event is lower. Do you agree with this? Can you tell me why? Because if some event I know if it is certain, then I have no ignorance. Okay? So as soon as the event has probability which is less than 1, and if I decrease this probability, my ignorance will increase. Okay? So in a sense that so if I quantify the amount of ignorance or amount of information, whatever you want to call, of some event whose probability is P, the probability of occurrence of that event. Here for example this probability of having the surface as water is 2/3. So if I quantify I of P as the amount of ignorance or amount of information of some event whose probability is P, then you see that this varies as 1 upon P. Is that clear? Okay? So this should vary as 1 upon P, because if I increase P, this probability, this will decrease the amount of ignorance. Okay? Sorry? Yeah, because it depends upon the probability. Yes, it depends upon the probability. This is the probability. Okay. Okay, so let me erase this part. Right. So now the question is, this probability P, you know that 0 less than equal to P less than equal to 1, because this is probability, right? So the question is, what will be the actual functional form of this information content, okay? What will be the actual functional form? Okay. So you know there are plenty of functions which will behave like this. Here comes certain properties, okay, that you will have to impose on this function. First of all, the information content IP, this is a continuous function. Of P. I mean, this is expected, like if I continuously decrease my probability, information content should increase continuously. Okay. So this is, I mean, generic idea, right? It should be a continuous function of P. This is additive function of P. So if I have two independent phenomena, independent events, let's say, okay, that means two events which do not influence each other, then the information contents of these two events, if I club them together, that means the total information content of these two events together, okay, that should be additive, because you know ignorance of two events, if they are independent, you know, ignorance will basically add up. Okay. So this is again a property of this function I of P. This should be additive function. Okay. So in other words, if I have the, let's say, probability of some event A is, say, it is P of A, and probability of another event which are independent, this is P of B, where A and B are independent, they don't influence each other, then this I of A and B, A, B together, or you can say A plus B, okay. So A and B together, this should be basically is equal to I of A plus I of B. Okay. This is additive function, right? So if I take these two assumptions on this I of P, which is the amount of ignorance, then one can prove, and this is what Claude Shannon has done. By the way, the information, classical information theory that I am talking about was developed by somebody called Claude Shannon. He came up first with a paper called A Mathematical Theory of Information, and then, you know, perhaps 1 year later, this is actually in 1948, he came up with this work called The Mathematical Theory of Information. Okay? Right? And what I am going to talk about, what I am talking about is about that word, The Mathematical Theory of Information. Okay? Right. And Claude Shannon, you know, he was an electrical engineer. Okay. Yes.
Regarding
Yes.
Suppose I have a lattice and I have probability of the particle being in any one of the positions on x-axis, and I have probability of the particle being any one of the positions on y-axis. Then the probability of the combined thing, won't it be multiplicative instead of being additive?
Yeah, that is multiplicative, but the question is that this is independent events, okay. So the here when you are talking about particle can move along x direction or it can move along y direction. Simultaneously it cannot move both along x and y direction, right.
So that would depend on the constraint of the particle. Particle could move.
No, no, classical particle, how can it move at a time on both the directions, okay.
Then suppose I look at it after some time.
Yes. Then also, classically you can have only one trajectory. You cannot have, more than one trajectory at a time.
No, I agree, but then the probability of the particle being any one of the lattices.
Yes, it will be product, but these events are not independent in this case.
But it can move independently next.
It can move independently, that is true, but if you look at the entire figure, entire picture, then it will not be independent. So here what I am talking about, let us say I toss a coin, okay, right, I will have some probability, right, and then I take another event, not about tossing a coin. So when I talk about this independent event means that the probability of occurrence of event A, in no way it can influence the probability of occurrence of event B and vice versa. In this case that you have given, it can influence. If the particle goes along x axis for a particular time, it cannot go along y axis.
Yes, I take your example.
Yes.
Toss the coin and roll the dice. Then also the probability is product.
That is probability product, but these two are not in, see, you are doing this thing in the same case, okay. So if I toss a coin and if I throw a die, joint probability is product, of course, joint probability is product, but here it is not joint probability, it is about two independent events, okay. So for example, maybe this is confusion is that, if I have to have some event A and or, okay, so I don't know how to use that, like, it is not that both of these will occur, either this will occur or this will occur, okay. So you can say or B, okay, either this will occur or this will occur, right. So then what will happen, these probabilities, okay. So maybe this notation is not correct, so it is, you can say A or B, okay. So these two are independent events, so their probabilities will add up. Sorry? No, it cannot go to 0. How can it go to 0? Question is, see, when we talk about events being independent, it is not linear independence. Whatever be the way you look at, they are independent. Okay, so by using these two properties, this continuous function of P and the additivity property, one can prove, and in fact this is what Shannon has shown, is that this I of P is basically a function, it has this functional form which is called logarithm with respect to base 2 of 1 upon P. Now this is not exact, this is up to some additive or multiplicative factor. Okay. You can add some factor, some term here, or you can multiply by some constant. Okay. But here I am not talking, I am not considering this factor, neither a factor, let us say called A, nor this constant B. So I am not taking that, just I am considering this. Okay. So from now onwards, this form of this IP is basically of this. So this is logarithm of 1 upon P with respect to base 2. And what is this base 2? Why this base 2? Because classical information, I can always, whatever information you can think about, I can always write it as a string of 0, 1, 1, 0 something, okay. Whatever information you tell me, I can digitize it and write it as a string of zeros and 1. And because it is only two values, zeros and 1, a bit, so this logarithm, this base of this comes out as 2, okay. So we say that this is the bit of information, okay, bit of information corresponding to this probability P, okay, right. So then so if I have events, let us say this is A1 event which occurs with probability P1, A2 event which occurs with probability P2, and so on, An event which occurs with probability Pn. So like you think of it like this coin tossing. I toss a coin, if head comes, let us say probability of head is let us say P, and probability of tail, let us say it is 1 minus P, because if I add these probabilities, sum over all these Pi's, this should be equal to 1, because sum of these probabilities, like here, this probability add up to 1, okay. So if this is the case, then for this event, IP1 is of course log of 1 by P1, here IP2 is log of 1 by P2, and so on, right. So the average information content, if I look at it, so the average information content of this set of all events, this thing, this will be basically sum over I is equal to 1 to n Pi log to the base 2 1 upon Pi. Do you agree with this? Right? This is the, can you see from the back this one? So this is the average information content. For each event, this is the information content, and each event occurs with these probabilities Pi. So therefore the average information content is this, okay, right. Is that clear? And this is what is known as Shannon entropy. Shannon entropy of this probability distribution. So this is the probability distribution P1, P2 up to Pn. As I said, from now onwards we will not care what particular event, what is the name of that event, we only look at their probabilities. Okay. So if somebody tells me that this is your probability distribution, then the information content of this probability distribution is this quantity. Okay. So this is the notation that we will use. H of P1, P2, Pn, this is equal to that quantity which is basically I is equal to 1 to n Pi log 2 Pi, right. Do you agree with that? Because if I take this log of 1 by P1, it will be log 1 minus log Pi, log 1 is 0, so therefore you will have this minus sign here, okay. So this is what is known as Shannon entropy. And this is the information content, okay, of this probability distribution, right. Okay, good. So now, what about the information content of certain event, like the sun will rise in the east? What is the information content? 0. Because the probability that sun will rise in the east is 1, and the remaining probabilities that sun will not rise in the east will be 0, and therefore if I put that here, it will be 0. Okay. So for certain event, the Shannon entropy is 0. What about the Shannon entropy of this statement that sun will rise in the west? What about the information? What about the Shannon entropy of that statement? Again 0, right? Because the probability that sun will rise in the west is 0. Okay, right? So from that you can figure out that this is again the, so for certain event or impossible event, Shannon entropy is 0. Okay, right? What is the maximum that this can have? Given a probability distribution, whatever be the probability distribution, what is the maximum value this can have? That means what is the maximum ignorance you can have when each event is equally probable, right? Okay, and that happens when this P1 is 1 upon n, P2 is 1 upon n, etc., Pn is 1 upon n. And in that case, so therefore this quantity is less than or equal to, what will be that? Minus of log 2 base n, right? How do you get that? Just put here Pi is equal to 1 upon n, you will get this. Okay. So this is the maximum that you can have. Okay. So if I take, let us say, just in the example of earth surface, whether it is water or land. Okay. So then this probability, so which is that probability of land, this is 1/3, and probability of water, this is 2/3. So what is the information content of this? This will be, can you tell me, minus 1/3 log to the base 2 1/3, and then minus 2/3 log to the base 2/3. This you can figure out. Okay. Will it be, is it a negative quantity or positive quantity? Positive quantity. How much will it be? Will it be greater than 1, less than 1? Less than 1. So whenever you have only 2 possibilities with probability, so like P and 1 minus P, only 2 possibilities. This is, it's called binary. So this is the binary Shannon entropy. So this is basically minus P log to the base 2P minus 1 minus P log to the base 1 minus P. So if I plot it, this is P and this is H of P1 minus P. Okay. So this is your 0, say this is 1, this is also 1. So this is your half. So I know that when P is equal to half, this is the maximum, okay, and which is basically log 2, and log 2 with respect to base 2 is 1. So you see that what will happen is it is 0, this is maximum, and again 0. So this is the plot of this binary Shannon entropy. Okay, it will increase, it is 0 here, P is equal to 0, at half this is maximum, which is 1, and at 1 it is again 0. Okay. Okay, good. Yes. There will be? Yeah, there is no minus. Yeah. Where is minus? No, no, this I have drawn. This is no minus. Ah, sorry, yeah, yeah. This is log 2, yes. Sorry, yeah. This is 2, yeah, right. There is no minus because, this is a positive quantity, yes. Okay, good. So now, let us try to interpret this Shannon entropy. Okay, I said that this is your information content. If you have some event, then let us try to interpret it. Okay, let us say that I have a coin, okay, bias coin. So probability of head is say P and probability of tail, let us say 1 minus P. Right? I mean P is equal to half means it is unbiased coin. Okay. Now let us toss this coin one after another. Okay. Or you can take n such coins each having this probability distribution and toss them simultaneously. It's up to you. Okay. So if I toss this coin n times, independently I do. Okay. So you can have, for example, initially the first one may be H1. H1 means in the first run it is head. Okay. Next one may be again H2. Third one may be T1, T3, fourth one may be H4, so on. Right. So I am tossing the coin one after another independently. So then the events maybe it will look like this. Okay. It may also look like, let's say T1, again this may be T2, then this is H3, T4, so on. Okay. So how many such possibilities will be there? If I do it n times? Sorry? How many possibilities? 2 power n, right? So 2 power n possibilities will be there, right? And if I look at, so this is, you can think of it as a string, okay? This is a string of head and tail, this is another string of head and tail. Okay. So what is the probability that this string will happen? So probability that this string will happen. What will be that? I said I toss the coin independently. Same coin, I toss it independently. What is the probability of such a string? Sorry? 1 by? One by 2 power n. Is that the case? This is not a unbiased coin, this is a biased coin. So it depends how many heads are there and how many tails are there, right? Okay. So if there are, let's say in this string, there are, let's say, m number of heads and of course n minus m number of tails, right? Then what will be the probability? Because I said I have done it independently. So the probability of occurring head is p. So this will be p to the power m into 1 minus p to the power n minus m. Do you agree with me? Okay. So this is the probability. So each such string, they are not equally probable. Okay. So they will happen with this kind of probability structure, right? Because it is not an unbiased coin. Okay, good. So this is fine. Now let us assume that this n, that means number of tossing I am doing is very large. N is much greater than 1. N is very large. Okay. Then how many times you would expect head there? If n is very large, how many times you would expect that head will happen? Roughly. Sorry? P times? P fraction of the total number of tossing. What is n times P, right? Okay. So n times P, this is the number of head in a typical sequence, typical string. And similarly n into 1 minus P, number of tail in a typical string, right? Is that clear? Okay. And this is how actually we figured out that this is the probability P and 1 minus P. I keep on tossing the coin many times and then look at how many times head has happened, how many times tail has happened, and from this frequentist approach you can figure out this. So if n is large, this is what you will have. Now do you think that this happens to every such string? Out of this 2 to the power n string, do you think that this will happen in every string? Yes or no? Is this question clear? So question is that typically, of course, if you look at a string, this is the structure. But is it the structure for every string? No? Why not? Sorry? Yes. If there are n heads, then it will be p to the power n. If there are n tails, it will be 1 minus p to the power n. So not every sequence will have this typical structure. Is that clear? Okay. Okay. But how many of these strings will have this structure? I understand that not all of these 2 to the power n string will have this structure. But next question is, how many of them will have these structures? Sorry? Yes, that is true. But my question is whether such a structure will happen in most of the cases or not. So there are 2 to the power n strings. Okay. If I choose a particular string, will it have such a structure or will it not have such a structure? So if a majority of this string will violate such a structure for large n, do you expect to have this probability distribution? So when I say this structure means, because n is large, there can be small deviation, that is fine. So it may not be np, it may be np plus minus epsilon, that is okay. Okay. So but the question is, if I choose randomly a sequence from this 2 to the power n, will it have such a structure or not? Or let me pose it in a different way. If it happens that for a randomly chosen sequence from this 2 to the power n sequence, this structure gets violated. Violated, in a big way, not just NP plus minus epsilon. I am not saying that. That is not a violation. If it happens, if it violates this structure, will you get this kind of probability distribution? Okay, let me ask you another question. How do you know that if I have a bias coin, the probability of having head is, let's say, 40% and probability of having tail, let's say, 60%? How do you know that? Yes, you repeat the experiment under independent conditions, right, many times, and take the frequency, and then in the limit of repeating the experiment many times, you will get these probabilities, right? So then, if such a structure is grossly violated, then you will never expect this kind of probability distribution. Okay? So this is why we say that if I choose a sequence, typically it will have this structure. Okay? When I say NP means, NP plus minus epsilon is fine. So typically it will have this structure, and those sequences are called typical sequences. Okay? So among these 2 to the power n sequences, or the strings, those of the strings, each of which has this property, are called typical sequences. Okay? Typical sequence, typical string, whatever you want to call. Right? Okay, good. Now next question is, so I choose a string from this 2 to the power n string. What is the probability that it will be a typical string? Not all these strings are typical, that we agreed. Right? So what is the probability that it will be a typical string? Any answer? So it means that how many of these sequences of the strings will have this structure? That means NP of them will be head, n into 1 minus p of them will be tail. So how many of these sequences? So the question is, how many of them will be typical sequences? How do I figure out?
Can't all the sequence be the typical sequence?
Yes, because
There are n very large number of them, and there is a possibility that all of them can be head, as you said, that might violate this. But when all of those happen to be head, you can just change the value of p and substitute over there. Then p will be 1 and 1 minus p will be 0, and np will give me n heads and 0 tails. So but that doesn't seem, all the sequence seem to obey this kind of structure.
so when I consider this is my given knowledge that head will occur with probability p and tail will occur with probability 1 minus p. I cannot change that.
Yes.
So this is my given fact. Based on that, I toss this coin. During the tossing of the coin, this structure should not change. This probability structure should not change. So this is given. Given that, if I toss it several times, m is very large, then of course there are sequences where all of them can be head. Okay, or maybe let's say 95% or whatever. Almost all of them are head. So those are not, because then it will be gross violation of.
But then, at that case, instantly the p and 1 minus p changes, no sir, for every sequence then.
No.
For example.
How can it change? This is what I said. This is a given fact.
Okay.
That it is a coin, probability of head is p and tail is 1 minus p. This is given. But when I toss the coin, this fact will not change.
But I get into a problem. So thing is, if I have 100 points, let's assume that 100 to be big enough. Okay, just for our convenience, we cannot take infinities. So I have 100 points, and what I do is that, okay, let me say you say that there is a chance that all of them might be hit as well. But at that time, the initial probability changes. Initially, I had 60-40. But after that, I have a chance where I'm at all the 100 of them might be hit. But at the time, the P changes.
No. This is the thing. The thing is that when we say that the probability of having A it means that I have solved, somebody has solved this one large number of times as an independent partition. And then look at the sequence of occurrence of this and sequence of occurrence. And this sequence, same number of branch of but in the limit of taking very large number of
You tend towards P.
so that is given. That given this fact, let's say that if I this is why it is important that you have to run the experiment several very large. If you do it more than that, may not be. So, so the point is that out of these things to be defined, how many of them are what means that I have n run out of n will be n and n is 1 minus and what is the number? Number is factorial n divided by n factorial n is 1 minus. You agree with me? This is the total number of n. So number of can you see that? So this is factorial n divided by n factorial n is 1 minus. Half length of it out of it n will be head and n is 1 minus. How much is it? So here it doesn't matter whether J will come first, P will come second. So this is the total. So this is the number of physical. What is the total number of physical? For it. Out of which number of how big is this number? How to do that? In other words, can I write it something like 2 to the power, let's say, in prime? Approximately. Let's see. Okay, to get an idea about so let us take its logarithm with respect to base. Why? Because I said that I try to compare it in power. So I take logarithm. Because here, so this will be log n factorial minus log where we need to use probability. So you'll have to use the Stalling approximation for this, and let me, yeah, so basically Stalling approximation tells you that this for large n, so n is very, very large, n, this is approximately equal to n log n minus n, right? Okay. So this is what is known as Stalling's approximation. Okay. So you use this here. So this will be therefore approximately n log 2 base n minus n, then minus, this is np log 2 np minus np, and then minus, is it, can you see this thing here? Okay. So this is n into 1 minus p log 2 n into 1 minus p, and then minus n into 1 minus p. Okay. So anyway, so if you do that, what you will get is something like n times h of p and 1 minus p. H of p and 1 minus p I have written, right? This is the binary Shannon entropy, right? So approximately for large n, log 2 of this is n into the Shannon entropy, 2-point Shannon entropy. Okay. So therefore, what is this quantity then, this number, what is that? So therefore you see that n factorial by np factorial and n into 1 minus p factorial, this is approximately 2 to the power n h of p and 1 minus p. Is that clear? Okay. So this is the number of typical sequences. Okay. So now the question is, I have 2 to the power n such sequence, I choose arbitrarily one sequence, what is the probability that it will be a typical sequence? Is this question clear? I have 2 to the power n sequences, out of which this is the number of typical sequences. I choose a sequence randomly from the set of 2 to the power n sequences. What is the probability that it will be a typical sequence? Sorry? This divided by 2 to the power n, right? That is the typical sequence. Okay, good. So therefore is this part, oh, this is not the okay. So let me erase this. So the probability that a sequence is typical, this is 2 to the power n h p 1 minus p divided by 2 to the power n, right? This is the probability. Okay. Right. Okay, good. So what is this good for? That you have this many typical sequences. What is it good for? Basically, if I now ask you the following question, that what is the total probability of typical sequences? There are 2 to the power n sequences, okay, and out of which this many are typical sequences. So the total probability, of typical sequences. This means you take the collection of typical sequences, what is the probability of that collection, okay, that is the question, right. So what will happen is that this total probability, basically it is approximately 1 for large n. Okay. So the total probability of these typical sequences will be close to 1. In fact, it will be closer and closer to 1 as you increase n. Okay. So what does it mean? It means that for very large number of such runs, a sequence will be more or less a typical sequence. If I choose a sequence arbitrarily, it will be more or less a typical sequence, right? Okay. Is that clear? So this is how do you reach that? Because you will have to take the total number of this is the total number of typical sequences, and multiply it by the probability of occurrence of each sequence. Okay. I am not going through the mathematics, but this is what you will see. I mean, ideally the point is that if I choose a sequence for very large n, it will be generally a typical sequence. I mean, this thing that H, etc., or T, etc., these are called atypical sequence. They will not happen. Okay. And why this is important? Let me tell you why this fact is important. Because now, let's say I will have to store data. What is the data? I will have to store the results of tossing this coin, okay, on a computer, or whatever you want to call. I want to store the data. So let's say I store H by this bit 0 and T by bit 1. Okay. So I want to store the data about the strings. How many data of how many strings I'll have to store? If I ask this question, do I have to store all the 2 to the power n strings, or can I do it with less number of storage space? Okay. So that is the question. And because if you take n to be very large, 2 to the power n is much larger, and in our computer we don't have those. However supercomputer you take, we don't have that many data space. So the question is that among these 2 to the power n sequences, how many of them, or which one I should store and which one I should neglect. So basically I should store only those typical sequences, and the remaining ones I just neglect. Okay. So what does it mean? It means that the sequences which are atypical, that means which do not have this property, that NP of them will be head, and n into 1 minus p will be tail. So this typical property is not there. Those sequences are atypical sequences, and those sequences I will not store. Why? Because the probability that a sequence is atypical is very less for large n. So I don't have to consider them. Okay. So if I store only the information of the typical sequences, once I store it, and then later part I can retrieve back. Okay. So basically I will store these many sequences, and remaining ones I forget. Later I can retrieve them exactly. I mean, provided where I store there is nothing happens there. Okay. So this is what I will store. This many sequences I will store. That means the typical sequences, and remaining one I will forget. Okay. Now the question is that Does it help? So with respect to 2 to the power n, how big is this number? Because if you see that this number is very much close to 2 to the power n, I mean there is no advantage we get. Okay? So the question is, how big is this number if n is very large? Because I am talking about large n, asymptotic limit. So as you can figure out from this plot that I said, this h of p and 1 minus p, at p equal to 0 and p equal to 1, this is 0, and p is equal to half, this is 1, right? So this will be 2 to the power n only when p is half. For all other p values, this h of p into 1 minus p will be less than 1. And when this is less than 1, let us say this is h of p and 1 minus p, let us say this is 0.8, let us say, right. So for large n, this 2 to the power n into 0.8 and 2 to the power n, what is that? It is 2 to the power minus n into 0.8. But for large n, this quantity, no, what is that? Sorry. What is that? Minus n into 0.2. So for large n, this quantity, you see that if started entropy 2.7 less than 1, then actually the total number of must be less than when is the time you don't get any advantage? When p is by storing the data, you have the idea. So now let us come back to interpretation of h of yeah. No. This is why you will have to take the total probability of the typical sequences is the number of typical sequences multiplied by probability of occurrence of individual typical sequences, right? Because they are equally probable. So that will not give you 0. That will give you 1 actually if you take n going to infinity. Okay, so what is so this I said that h of p and 1 minus p, this is the Shannon entropy, 2-point Shannon entropy. So we learned that this is the amount of information. Okay. Now here is another interpretation. So interpretation is that if I want to store the data of a large sequence of zeros and ones, zeros or 1 or head or tail, whatever you call, zeros and ones, okay, a sequence of zeros and ones, and here you have a large number of sequence also, and the sequence length is also large. If I want to store that on computer or whatever, so the question is that what will be the length of the bit string, this is bit string, that will be required. So the length is basically n into h of p and 1 minus p. If I know that the probability of occurrence of individual 0 is p and probability of occurrence of 1 is 1 minus p. So then the length of this sequence that will be required to store these data about this sequence is n times h of p 1 minus p, because this is what I said about the, so you will have to store only the typical sequence. So this is the length of this bit string that you will require to store, right? And for single bit, how many, what will be the length? Basically h, because you know your total length was n. So n into h p 1 minus p is the length of the typical sequence. I mean, sorry, this is the number of bits that you will require to store the typical sequences. So per bit, what is the length that you will require? H into 1 minus p, and this is basically a fraction. Okay, most of the times it is a fraction. So you see that in terms of data storage, you have this advantage, right? Rather than, you know, writing down all the sequences, this is enough. N into HP 1 minus P is enough. So in this sense, you can interpret that what is the Shannon entropy? Shannon entropy is the amount of bits or length of the bits, okay, that you will require to store the data of n bit string for large n. So n into HP 1 minus P number of, this is the length of the string that you will require to store, okay, in order to store data about n bit string. Okay, is this clear? So in order to store data of n bit string of zeros and ones, what you need is n into HP 1 minus P length of bit string to store the data, and that you can also later part reliably decode. Okay. So in this sense, Shannon entropy is also a kind of data compression. You are compressing the data, right, because this is less than 1 generally. So this Shannon entropy, you can think of it as the data compression limit of storing information and thereby reliably also decoding it. Okay, okay, good. So this is what is known as Shannon's data compression theorem. Okay, so whatever we talked about is basically Shannon's data compression theorem. So Shannon's data compression theorem tells you that if you want to store information about n bit string where n is large, where the string occurs with these probabilities, then n into HP 1 minus P will be the length of the string that you require to store the data reliably, so that later part you can also decode that, retrieve that data. Okay. So I told you about this 2-point function, but this is generally true. So let me see. So if you have, let's say, these probabilities of this event, let's say it is x1 probability, this probability happens with p1, probability of x2 happens with p2, and similarly probability of, so you can have n events, so this is pn, so that sum over I is equal to 1 to n pi, this is 1. So instead of binary event, you can have n, outcome event, if this is the case, and then you want to store information about the values like this, x1, say, I call the value of this, so this is, let me call it as, okay, so maybe I should introduce. So are you familiar with the random variable? Okay, so like this, head and tail, this is also, it's a random variable x which will be head, and this probability is p, and then the random variable x will be tail with probability 1 minus p. Similarly, this is a generalization of it. Okay, so you say that instead of x1, let's say x is equal to x1, x is equal to x2, and x is equal to x. Right? probability of which we have to time it. Now I do the experiment where this is the first time I do that, like tossing a coin. I do this experiment first time, second time, third time, so on and so forth. N times or n times, whatever you want to call. So I do this, let's say n times. N times running the experiment. And this is, we do it independently. This is important. So then you see that the sequences will be something like, the H1, the first one, and second one can be H2, what it may be H3. Yeah? And the probability of that, so this is independent here, so this will be 1, and then you can again ask the question that what is the length of the bit string that is required to store the data about this thing. I want to do that. Okay, so then you see that same thing you can do. I will not go into the group. Basically, you have to see that total number typical sequence. Part in rate of 1. So this is just a generalization of whatever I told. So total number of typical sequences in this experiment, and you can again interpret. So this is the channel entropy of this problem. You can again interpret. Right. So the channel data compression theorem tells you that if I want to store data about values of random variables which I run independently several times, large number of times, then the length of this thing is for the length of this thing n times so that is the important thing that one might ask, what if I don't take n times the 1 to n? This many, this is the length of it. What if I take less than this? What will happen? If I take more than this, of course, nothing will happen. But if I take less than this, like in the case of coin, what if I take, let's say, n times 8, 3 and 1 minus. I'll take not this, but something less than 10 times 1, 1. Can I store the data reliably? Can do, but no. So this is the bare minimum that similarly here. This is the bare minimum that use less than size of this picture, then we do right. I think I data compression, you are somehow ignoring the atypical sequences which are not useful for your problem. Redundant sequences you are ignoring. So the atypical sequences are redundant. Next thing what I am going to talk about is channels. If I have noisy channels to send information, like noisy telephone, if I want to send information reliably from one place to another, we will see that like that to encode data and decode data. So the channel data competence theorem tells you how to compress the data so that you will use the bare minimum. And then channel capacity tells you that how to use redundancy, change information from one place to another place in a reliable manner, even if your channel is noisy. Right? So these are kind of hypotheses. So next time I'll talk about classical channel capacity. Thank you.
T is waiting outside, so you need to actually approach process device even though we can go and reconvene at 11:40. Okay, this clock is 7 minutes slow, so real time 11:40 we reconvene. Okay, yes. Thanks. Oh, by the way, I did not say, I hope actually you all know Varuni and Mani, right? So in case if you have any questions for reimbursement, etc., you have to contact them for certificates, reimbursement, everything. Whoever is coming from outside. You know, there was a lady outside and a man outside who was distributing these books and taking your signatures. So you just contact them for reimbursement, certificate, or any other queries. Okay. Thanks.
idea is to introduce you to the transformation. And then to introduce you and then to set such transformation maintain So what are these transformations? What do they do? What do they transform? So in quantum mechanics, the basic thing is state of a system. There is a physical system. How do you denote the state of a system? All of you have done quantum mechanics. So, wave function. But wave function is actually a representation in a particular space. So, we don't want to specify any particular representation. We want to put it in the abstract notation. What is that notation? Are you? Huh? Dirac notation, right? You can denote the state of a system, let's say, by what is called as a ket. Okay? If you want a representation of this ket in the position space, you can do that. You would have done that in quantum mechanics. And then you will say psi is then a function of x, position. Psi of x. That's your position space representation. You can get it from this abstract ket space. You can also go to the momentum space, project it onto the momentum space. That will be psi of p, right? So, we don't want to confine ourselves to any one representation. So, we just denote that this is the state of a system. It has all the information about the system. It's actually a vector space, and in fact here we call this as the Hilbert space. Okay? In particular, if you multiply this state, a ket, by a complex number C, that also denotes the state of the same system. So it is not, you can multiply it by any complex number, it equally well denotes the state of the system. Hence, sometimes it's called as the ray space. Okay. So it's not important what the magnitude is, and therefore often, as you have seen in your quantum mechanics, we just use normalized states. The dual to the ket is denoted as a bra state. This resides in the dual space to this. And you can define what is called as an inner product between two vectors. Okay? So that is a number. Let's say there is a ket, there is a bra psi and a ket phi. We call this as the inner product between two vector, a vector and the dual of another vector. This is in general greater than or equal to 0. It's a complex number, When it is equal to 0, what do you call it? They are orthogonal. Oh, good. So therefore, we define the inner product between two states. The way to imagine it is like, suppose you have two vectors in ordinary space. The scalar product between those two vectors is a number, right? And that is like the inner product between two vectors in this three-dimensional space. This is the inner product between phi and the ket and the bra, and that is greater than or equal to 0. Okay? So this is what we need. Much of these things will be done in detail by Professor Ravindran. So I will not spend too much time on this. This is purely to set the notation for what we are going to do next. Okay. And the length of this vector is simply the inner product of the vector with itself. So this is the length. Of the vector. Okay? And these are the states, and in any experiment, when you want to observe the state, depending on the observations that you are interested in, your measurement will involve certain apparatus. So that apparatus will act on the system and go to the so the mathematical statement process of observation, what we do in lab, is mathematically put in the form of an operator corresponding to an observer acting on the state. And obviously when something acts on the state, that means in a measurement that I do something to the system, right? So the act of measurement can be represented by the following. Suppose there is an operator corresponding to an observable, any observable. Since we haven't specified what the system is, we don't have to specify what the observable is. But it corresponds to an observable. This acts on the state, right? And in general, it will give you the new state by what is the property of the operator, and this is precisely the way we do transformation. There is a measuring operator, that and that. Okay. What we are interested in specifically in quantum mechanics is not any operator, but a particular kind of operator. What is that? Hermitian. Why Hermitian? Eigenvalues are real because you want it to correspond to your measurement. So if eigenvalues are the measured in certain specific case. So therefore that one. Therefore, now most cases they are operators which are so in general we are interested in operators which are I keep putting this tab, but slowly I will not put it once you are familiar with the station and once you know that I am dealing with. So, what does this mean? It means it's Hermitian. That means O is, let's say, you take a consider a representation of O, it may be a complex quantity and then transpose the rows and columns. That is a Hermitian conjugate. For those who are not familiar, because there are many undergraduates here, if you don't understand something, just put your hand up and ask me, okay? But all these things will be done again in the quantum mechanics course by Professor Ravindra. So we are interested in particular in Hermitian operators. There are special cases where this equation, the right hand side actually gives you back the same state. Not exactly the same state, may be multiplied by some number. So therefore, suppose this some A times psi, where A is a number, real number, okay? So then, what do you call this? A is called the eigenvalue. Then this psi is an eigenstate of the operator O. And in particular, if A is a real number, not some other number, then this is a Hermitian operator, because Hermitian operators have real eigenvalues. Okay. Now you can also take any arbitrary space. Suppose you have an operator and you have a set of eigenstates like this. Then you can express any arbitrary state of the system where the psi-ens are eigenstates of some Hermitian operator corresponding to this system. Okay. So this is the completeness relation, and these A-ens are the expansion coefficient. Any arbitrary state can be expanded in terms of a complete set of states corresponding to an operator. Superposition is, that will, as I said, I am skipping many things. So superposition is given to you in the beginning itself. So superposition of a ket A with ket B plus ket B is also a ket, a state of the system. Okay. So that is, I should have said it in the beginning, but that's okay. That's true. That comes right here when you define the space. In the Hilbert space, you take any two states and then you combine them, it also gives you a state of the system. It's like superposition of vectors. You know, you add two vectors, you will get a third vector. Okay, that's also part of the same set. Yeah. Okay. So this is as far as the state of the system is concerned, and this O operator is a transformation. Okay, it transforms the state. Okay. But there are certain types of transformations that we are interested in quantum mechanics. If you want to describe the dynamics, how the system changes in time, that is what we are interested. See, in classical mechanics, what is the fundamental thing? Equations of motion. What do equations of motion do? You know the state of the system which is specified at some time. Take Newton's equation. Okay? You call that initial condition. Given that, equations of motion will tell you, or equation of motion if it's one dimension, or equations of motion if it's many dimensions, many particles, so it can be as complicated. But given the initial state which is completely specified, then the equations of motion determine the state of the system at all times, classically. It's a deterministic system. The thing in quantum mechanics is slightly different. There, the observable themselves keep changing, and they keep, we know how to dynamically evolve them. Here we look at how the state of the system evolves. Okay? So the state of the system, suppose you have psi at time 0. It can be t equals some t naught. I just put it as 0. I start the clock at that time. I want to know how the system evolves. What is the dynamical evolution of the system? This is a fundamental question that we try to answer. Whether it's quantum dynamics or classical dynamics, that is the question. So, let us say there is a transformation u which takes it to psi at time t. It's an operator which takes the system at time t equal to 0. So what kind of an operator is it? In order to find out, we invoke the fundamental principle. We have already defined what is called as inner product. So the same operator operating on psi at time takes psi at another operator. So how do we so that yeah. So the information content in phi and psi is there in the inner product. If there is nothing else that is happening, I'm just looking at it, I'm not looking at any interaction. Okay? If you just leave that, the two systems there, the inner product cannot change. So for example, if the inner product is between psi at 0 and psi at 0, that is actually the probability of that system. That comes with the interpretation of the psi in quantum mechanics. But that cannot change over time if the two systems are isolated and sitting there, right? So therefore, if this is a fundamental principle, that information content does not change over time. There is nothing else that is acting on it, so therefore it doesn't change. It is just a time evolution. So, but then this is this psi of t, these vector transform as u dagger. Remember, this is u and I am taking the conjugate, and this is u phi, sorry, this is equal to psi at 0 and time 0. Okay? Right? I should have mentioned that O acting on psi, O dagger, the bra vector transforms as O dagger. Yeah, I am using that formulation. Okay. So what do you get from this? What do you conclude from this? U dagger U is equal to identity, correct. So these U's are of course time dependent, that is how they are transforming the system. So U dagger U is equal to identity. So what do you call the U? So such matrices, such operators are called as unitary operators. So U is a unitary operator. But remember, this time translation is a continuous transformation. It's not discrete. Time flows continuously. So I can make this transformation. Any finite time translation can be obtained by incrementally doing this translation in time by very, very small amounts, tiny amounts. I take it all the way. Okay? So I can generate the finite transformation continuously starting from identity and making many infinitesimal transformations. Okay? So that is true of any continuous transformation, and in particular that is also true of this unitary transformation. In particular, sorry. Sorry?
Could you repeat the argument for keeping the inner product?
You mean this argument? This one. Huh? So what I am saying is that this is a fundamental principle, that with time evolution the information content will not change. Right? Because there is nothing, it's simply evolving in time. So whatever change is happening in phi is also happening in psi. So the inner product, it's like saying, huh? That is if you take the same system. Okay? This is the inner product between 2, phi and psi. But yes, it leads to the conservation of probability. Huh? Both are? Isolated system. So therefore, that information cannot change just because it's evolving in time. Huh? No, I start, no, here there is no, we are not talking about properties of time at all. I am starting at time t equal to 0 and evolving it that I can start the clock at any time. So in some sense it's, if you put instead of 0, if you put t naught, that's also fine. So, but the point is that this is invariant under time translation. And that's all we are using. Okay? I am not bringing in relativity properties of time, that's a separate question. Okay? All right? So this is a fundamental principle that we have to use here, that there is no loss of information as far as the inner product is concerned. You will see what all things follow from that. Okay? Now this is then a unitary operator, and any unitary operator can be represented as e to the power some, let me be careful here, I epsilon times h. Since u dagger u is equal to identity, that means e to the power I epsilon h minus h dagger is equal to identity. Just some representation. I want to write it in this form. This form will keep reappearing in many places. So I just write the unitary operator in terms of this, where this h is another operator, provides a representation for this unitary operator, but this h is Hermitian. because u dagger u is equal to 1, and using this representation, I just take I epsilon h minus h dagger, and therefore I can write this h equals h dagger because of this property. Okay? So you can generate a unitary transformation using a Hermitian operator, but in this exponential form. Okay? So this h happens to be Hermitian. I will use this representation now to write this unitary operator Suppose I make this epsilon very small. Of course, this epsilon has to be, I'll change the notation. I'll write it as I t times h, because it's time evolution. For small times, I can expand this exponential and write it as E1 identity plus I. Suppose I make a very small time evolution, delta t is very small, then I can write this as I delta t times h. I can make delta t as small as possible and expand the exponential up to first order. Okay? So this is I would have liked it with a negative sign. Huh? Yeah. Here.
Because u dagger u will become minus I t h minus h dagger.
Yeah, correct. I should be a negative sign. Thank you. Right?
No, sir. The negative should be, that must be positive, sir. Only then the down can be negative.
No, this will always be true. Here it should be positive.
Ah, yes, sir.
Okay? Then this is you are saying this should be minus
Yes,
IT
minus,
H dagger minus
The
H.
thing is correct, sir.
But
down, yeah.
this is whether it's H minus H dagger or H dagger minus H.
So you're saying about the negative sign, so
Yeah?
there must be a
Yeah.
negative.
Okay. So now what I want is the following thing. I want it to be minus ITH. Is that correct? Yes, ITH. You will see why I want it like this. Okay? Then nothing will change here. And this, I can write this as minus this thing. So this H is now a Hermitian operator, which is the generator of this unitary transformation. Okay? So now I want to consider this infinite evolution operating on the state psi. Okay? So if I take, can I be seen here? Yeah. So let me consider the state at time t. Okay? And I want to evolve it for an infinitesimal amount of time taking it to psi of t plus delta t. So, not necessary to write this, it's obvious. You will see what it is. I evolve the state for an infinitesimal time delta t. So, that is psi of t plus delta t is equal to 1 minus I okay. This is the infinitesimal transformation on the state psi of t. So, now what I do is I take this over here and I will write this as psi of t plus delta t minus psi of t okay. Take this delta t to this denominator here. So, this is I psi of t delta t minus all I am doing is an infinitesimal transformation. I want to see how the states transform under this infinitesimal transformations. And delta t is in my hand, I can make it as small as possible, so that my expansion becomes more and more accurate. I take the limit delta t going to 0. So, what do you get? I, what is this? It's a partial derivative of time in the limit, right? So, this is so the generator of the unitary transformation determines the equation whose solution gives you the time evolution of the ket psi. What is that equation called? That is the Schrodinger equation. So, remember, all that we have used is this no information loss, right? Then you have the unitary transformation. Express it, the unitary transformation in terms of the generator of the unitary transformation, which is H. It's called generator in the sense that you can make this transformation as small as possible in terms of this H and use it to generate any finite unitary transformation. So, the name generator just indicates that, right? Then from this we want to know the infinitesimal evolution of this state. So, we use this form, okay, because any finite transformation can be generated by repeated application of this. So, therefore, we can just use this for any small amount of time, and in the limit this delta t going to 0, is this Schrodinger equation? Is there some problem with this? Huh? Note that H has dimension 1 by t. So I can't give it a name yet, right? Somewhere I have missed out on dimension. If I want to call it as Hamiltonian, then classically we know that the Hamiltonian has the dimensions of energy, right? So that is not matched here, right? There is no matching of dimensions of this if I want to call H as the Hamiltonian. But I would like to relate this H to a physical quantity, and I want to relate it to the Hamiltonian, classical Hamiltonian, which has the dimensions of energy. In order to do that, all I have to do is introduce a constant in this transformation to make the dimensions agree. See, I can simply say that this operator has inverse time dimension. But I don't want to do that, but I want to relate this H to something that is observable. And that observable is energy, right? So in order to do that, I will introduce a constant which matches the dimension. What is it? Yeah, what is available to me is the Planck's constant. Just one single constant, it will make it dimensionally quotient. So I will just say this is I by H bar. I will introduce that, and here I will introduce I by H bar. See, if once I interpret H as energy, I can make the dimensions agree with a constant. Scaling with a constant is always possible. So therefore, I do that, and I will put H bar here. Now H bar is action, MLT minus 1 over T, it's MLT minus 2 in dimensions, and the energy dimension is MLT minus 2. So now they are all matched. Now you can call this as Schrodinger equation. And call this H as the familiar Hamiltonian. We will use the name Hamiltonian. It has dimensions of energy. Okay? And the solutions of this equation determine how the psi evolves in time for a given Hamiltonian of the system. So the Hamiltonian specifies the system, and from that the time evolution comes as the solution of this equation. But we are also interested in how physical quantities change over time. Okay? So the physical quantities are defined. I will not go into the detail here. It will be done in your basic quantum mechanics course, which Ravindran is going to do. But the important quantity there is the expectation value. So let's define what is an expectation value. Consider any operator A, okay, its expectation value is defined by the following quantity, psi between two states, A and phi. Oh, expectation value, psi, sorry. Okay, we call this as the expectation value of the operator A. So in general, in quantum mechanics, this A might be an operator for momentum, angular momentum. So then the expectation value is the one that is measured. It is relatable to the measured quantities. So we want to know how this expectation value changes. So usually this is denoted by A. The meaning of that bracket is simply this. How does this change? Let's do that. What is the time evolution? Total time evolution of this operator A. We are interested in the expectation value, so therefore put the brackets. So this is equal to partial time operating on this, because there are three quantities which are dependent on time. So if the operator has an explicit dependence on time, then you have to add this term. If not, you can leave it out. Okay? Now this we know, this from the Schrodinger equation, but now you have to conjugate the whole thing. Therefore, you will have minus IH bar on this side, which you take it to that side, IH bar H. It becomes H psi, right? So, and H is Hamiltonian is Hermitian, so H dagger is H. So, therefore, what you will get is minus I by H bar. Do this. Positive. Check it. Anyway, I'll change it, but please all of you check the signs and other things. Okay? And this of course will be remain the same. So therefore, I can write the operator equation. Finally, it should be of this form. dA by dt is equal to psi commutator A comma H please check this plus the explicit time dependence psi psi. So this is the equation. Have I done it correctly? I should also get a IH bar here, right? Okay. Now, if there is no explicit time dependence, that is what the case that I am interested in, I will remove this term, and this is the equation for the evolution of the expectation value. So normally we write it in the operator form, where we write it as dA by dt is equal to the commutator A comma H. This is the operator equation, which means that the expectation values have actually this form. Okay? Please check whether it's A comma H or H comma A. I will leave it as an exercise. Let me. Yeah. Okay. You can work out all these steps, they are straightforward, and I would like you to check every equation that I am writing. Okay. So this equation is very important because suppose this operator commutes with the Hamiltonian. Suppose this commutator is 0. Sorry, what is the definition of this? It's simply AH minus HA. That's the definition of the commutator. So this notation is a shorthand notation for this, and it's called a commutator. Suppose this is equal to 0, that means this operator commutes with the Hamiltonian. Okay? Then what happens? Yes, it becomes time independent. So if the expectation value, if some measurable does not change with time as the system evolves, what do you call that? There is a physical quantity which does not change, which remains constant as the system evolves. It's a conserved quantity. So therefore, this operator is conserved if this commutator is equal to 0. Okay? So if you say A is conserved, or you say it's a constant of motion. So where have you seen this before? In classical mechanics. In classical mechanics, what is it? It's the Poisson bracket. So in fact, this was the route Dirac used for quantization. He noticed the structure of the Poisson bracket, and then the route to quantization was to replace the Poisson bracket by commutator brackets for operators. Okay, so that's the procedure which Dirac used, and in fact, if you see these equations and go back to classical mechanics and check Poisson bracket formulation of equations of motion, you will find that wherever you have Poisson brackets, you can replace it by the commutator brackets in quantum mechanics. It's a restatement of the correspondence principle. Okay? So, A is then, if the commutator is 0, A is a constant of motion. So now that we are talking about constant of motion, how do they arise? Is there anything that we can say which leads to the constant of motion? Okay. So there, now let's talk about symmetries. So what we have done until now is I have defined what a system is and how the system changes, and in particular how the system changes under time evolution, and the fact that information content is the same, should remain the same. We show that that principle leads automatically to the Schrodinger equation, or you can also say it leads to the operator equation. They are equivalent. We have used that here. So these are different descriptions of the same dynamics. But that also leads us to define what is a constant of motion, how it arises when an operator commutes with the Hamiltonian. So what is the general principle behind the existence of constants of motion? So in fact they are related to certain symmetry principles. Okay. So I will just digress a little bit to classical mechanics. In classical mechanics we have, and the same applies, we can take it over to the quantum mechanics. So we are now discussing symmetries. So this is done. Now we are here. As you know, classical mechanics is formulated. You can use different formulations. Of course, there is the Newtonian formulation, the Lagrangian, the Hamiltonian, anything else? You can do classical mechanics using any one of these formalisms, right? Anything else you know? You can also use the Hamilton-Jacobi formulation, but that I don't think they will do it in undergraduate class, I am not sure. These are all different descriptions available for the same phenomenon. The fundamental thing is all these descriptions lead to equations of motion. Same equation of motion. For a given system, if it obeys Newton's law, Newton's equation, Lagrangian mechanics also gives you the same Newton's equation. Hamiltonian mechanics also gives you the same equation of motion. So the fundamental thing is equation of motion. You arrive at the equation of motion from different points of view or different standpoints. But why do you need these different standpoints if you can do with equation? Equation of motion or equations of motion depending on the dimensions. Why do you need this Lagrangian formulation, Hamiltonian formulation? If you can do with Newtonian formulation, why? What is the advantage? You can guess, I don't mind. Yeah. Okay. Yeah. Okay. So more or less you are there. Let me put it in the following way. It depends on what you want, what you are looking at the system. Okay. So for example, oldest is of course the Newtonian equations of motion. Okay. But if you is everyone familiar with the Lagrangian? What is a Lagrangian? No, have you done? Anybody who doesn't know anything about Lagrangian has not done? You have not done. Okay. So the Lagrangian starts from, is just a capsule, 1 minute description for you, for those who don't know. How do you arrive at the Lagrangian formulation? It starts with the most basic principle that if you go from point A to point B, you can define what is called as an action. Yes, which is given as an integral along this some arbitrary path from A to B of a function L called the Lagrangian, and which is a function of the position variable along the path, call it x, velocity x dot, and time. Okay? You can define it for any path. Okay? So, when you integrate over this function from A to B, that gives you what is called as the action. You can choose any arbitrary curve between A and B and you can define this. But then what is a physical path? What is the physical, the system takes from A to B? Given a system, how does it go from A to B? There is one single path. But what is that physical path? That physical path is the one which obeys what is called as the action principle. Delta S is an extremum. Okay? In fact, we generally say it should be minimum, but the statement is actually delta S is equal to 0. This is called as the action principle. And the L that from this you can obtain this procedure, this extremization procedure will lead to an equation of motion in terms of this function L along the physical path. Okay? And that is dy dt of delta L by delta x dot minus partial derivative equal to 0. Okay? Now, here comes the advantage of the Lagrangian mechanics. That once you, for a given system, you can write down what this Lagrangian function is. You can determine what it is. For all mechanical systems, it's kinetic energy minus potential energy. It takes that form, but it need not be that form. Okay? So what it says is that once you have the Lagrangian, doesn't matter what system it is, the equations of motion always have this form. So somebody mentioned here that if you take Newtonian equations, depending on which frame you are, equations of motion take different forms. You don't know which is the best, which is not the best. So you have to go keep on transforming whatever you want. But the advantage with the Lagrangian mechanics is no matter what the system is, the equations of motion are always derived from the Lagrangian equation. This form does not change from system to system. It's the same. Okay? And another advantage with the Lagrangian formulation, and when you take a particular Lagrangian here and then evaluate this, what you get is Newton's equation. Okay? So that is what I meant by saying you will always get the same equation. These are fundamental. Independent of the formulation, you will get this. And similarly, in the Hamiltonian formulation, in order differential equation, like this is a second order differential equation, you will get a set of two first order differential equations for each degree of freedom. The advantage of the first order differential equation is that you can use it to define phase space and the evolution in the phase space. The language of phase space is very natural in Hamiltonian mechanics. And then you can trace the motion of the system along a phase curve, which is unique for every time evolution. Okay? So there are some beautiful things you can do in the phase space that requires Hamiltonian mechanics. There are some nice things which you can do with Lagrangian. In fact, it's a very beautiful thing because this action principle, even though it originated in dynamics, it's the most general principle. You can go to electrodynamics, you can define an action principle, get Maxwell's equations. You can go to standard model of particle physics, write the Lagrangian, and then use the action principle and get all the equations of motion. So the action principle, though it was first used in mechanics, it is the most general principle of law of physics. that any physical system follows the least action or extremum of action. This is the least action principle in mechanics, but even though it originated in mechanics, it is true in all of physics, in any area. Quantum field theory, you can start with the Lagrange action principle, write the action and get the equations of motion. Okay. So that is the advantage of this Lagrangian mechanics, but there is something else that is very beautiful about this Lagrangian thing. This is stated in terms of a theorem, and that theorem is called, it is related to symmetries, and the theorem is Emmy-Noether's theorem. How many of you have heard of Emmy-Noether's theorem? Good, very good. I'll state it. How many of you have heard about Emmy-Noether? She was one of the greatest mathematicians of early 20th century. Noether's theorem. Sorry? You can write the action principle in terms of Hamiltonian also. Yes, you can do that. What we do in the Lagrangian formulation, what we do is that we get to Hamiltonian from the Lagrangian. Yeah. Yeah, that's right. So, correct. Because Hamiltonian is useful in describing the phase space dynamics. For that, first you have to define momentum. Without defining momentum, you cannot get to Hamiltonian. So that takes you to the phase space, but you can independently start with Hamiltonian mechanics as first order set of first order equations. You define a phase space which is momentum and position as your 2n dimensional phase space for n degrees of freedom, and then you can start with first order equations in that. Okay. So that has a beauty of its own, and you can, I discuss it usually in classical mechanics, that approach. I start by that, the phase space approach. But in Lagrangian mechanics, you can go from Lagrangian to the Hamiltonian. It's actually a simple Legendre transformation. So you can write it in terms of either of them. But the starting point is the Lagrangian, because that's how we get the equations of motion. Okay. So, yeah. So the beauty of this Lagrangian is that the Noether's theorem, it states that if the Lagrangian is invariant, under a continuous transformation, then that invariance leads to a conserved quantity. Okay. This is the Noether's theorem in classical mechanics, but this holds good in even when you go to quantum mechanics. So when you say Lagrangian is invariant, it means it's symmetric. It's symmetric under a certain transformation. So what does symmetry mean here? That if the laws of physics don't change under a certain transformation, then you call it has a symmetry transformation. Okay. So, for example, if you take this Lagrangian, which is in general, I am just using one dimension, but you can extend the dimensions as much as you want. It is a function of, let us say, x dot and t in general. But suppose, let us take t out, there is no explicit time dependence, it is just a function of x and x dot. Okay. So, from the equation you see that if it is independent of x, L is only a function of x dot, independent of x. So, for example, L is simply a free particle with kinetic energy, then it is half mx dot square L, right. So, it is independent of x. What does it lead to? It leads to, if you use the equation of motion, it leads to the following, that if L is only a function of x dot, then d by dt, equation of motion tells you that along the physical path is equal to 0. What does it mean? It means that this delta L by delta x dot is a constant of motion. And we call it the momentum. The definition of momentum, this is nothing but P. So, what is the symmetry here? It is the space translation. And I can take this system, which is only a function of x dot, put it at any space point and start the dynamics. Okay? So, it is independent of x. So, then that such a system, momentum is conserved. Okay. Right? A free particle has only kinetic energy, and then if there is nothing else, no force acting, it will continue to move with the same momentum for all times. So, it is a constant of motion. So, the space translation invariance leads to momentum conservation. That is a symmetry. Okay. And this is a fundamental symmetry, it is not going to change when you go to quantum mechanics. Similarly, what about time translation? Yes, but we have to define energy through that. Here, since I called it as x, you can take x as position, but in some other Lagrangian, x may not be position. Like if you go to Lagrangian in electrodynamics, it will be function of some fields. Okay? So, it's I am just giving you this as an example of an invariance. So, if you look at the time translation, then you get the following thing. Let us take the total time derivative of L. I don't, the L is a function of x and x dot, but no explicit time dependence. I can put it, let me put it initially. What is this? This delta L by delta x dot plus delta L by delta x dot x double dot plus partial derivative with respect to time. So, I will use the equation of motion and write this as okay, combining various terms, you get this. So now I get the following thing, which is d by dt of L minus, what is delta L by delta x dot? It's momentum P. So L x times P is equal to 0. Huh? I have some problem with my ear, so
Won't it be delta L by delta x dot times x dot?
this is okay. This is okay. This is x double dot delta L by delta t. No explicit dependence on time. Okay. So then I take this and I use the equation of motion. Okay. If I use the equation of motion, I can replace this partial derivative with respect to x by the time derivative of this quantity. Correct. So then that is the definition of momentum. It's the conserved quantity.
No, the line after this.
X dot. Correct. Thank you. Yeah. Correct. Thank you very much. So this is equal to 0. So therefore, the time translation, when it's not explicitly dependent on time, gives you this conserved quantity, which is, I call this as E, which is L minus xp dot. Actually, it's written as xp dot minus L. Okay. Both are true, but the definition of energy is x dot p minus L. This is the definition of energy. For any mechanical system, it turns out to be energy, right? X dot p minus L. So for example, I'll give you a Lagrangian in one dimension. X dot is half mv squared kinetic energy, right? M x dot square, it's t minus v, it turns out to be t minus v, any arbitrary potential in one dimension. Okay, that's the form of a Lagrangian of a particle moving in a potential in one dimension. Okay, suppose you take that, then you put it here. This momentum p is mx dot, so this is mx dot squared minus half mx dot square plus v of x, and this is half m x dot square plus v of x, which is nothing but the energy of the system. That is why we call it energy, but in fact for some systems this may not have the interpretation of energy at all. But in general we define this as energy because in normal mechanical systems it corresponds to energy. So the continuous transformations, invariance of the Lagrangian under this continuous transformation leads to a conserved quantity, a constant of motion. Yeah. Oh, that you take any Lagrangian which is not quadratic, you try to do that, then it won't be energy, right. For general mechanical systems with the Lagrangian, where Lagrangian is of the form T minus V, where T is kinetic energy, V is potential energy. For most mechanical systems that form works, and then you will have energy equal to T plus V. In fact, we called it energy simply because we started with the mechanical systems, but when you generalize it, it's not necessarily the interpretation of energy. Huh? Non-linear? Say it again, please.
So if it is a non-linear dynamics like double pendulum, it works.
Yeah. In classical mechanics, this always. Here it is, we are not assuming whether the system is linear or non-linear. Nothing has been assumed. Yeah. So for example, you can take things like Lorentz attractor, okay, as a mechanical system, and then try to work it out. If you can write a Lagrangian for the system, then you can follow this. Yeah.
So the last step, sir.
This step.
Yeah.
Because this is d by dt is equal to d by dt of this plus x dot, right?
Okay,
so I can take over this to this side. So it's d by dt of L minus x dot.
That
yeah.
Taking
yeah.
to the
I have
LHS,
taken it to the. In fact, I should take it to that side, so that it's x dot p minus L. So then the energy will be positive. Otherwise, it becomes negative, and it won't have the interpretation of energy. So it's a convention that dictates whether you take L minus x dot p or x dot p minus L. Okay. Yeah. So this is the property of continuous transformation, but in quantum mechanics, we not only have continuous transformation, but we also have discrete transformations which play a role. So for example, if you look at Newton's equations, if you take t to minus t, it's invariant, but there is no consequence. All that it happens is that you can work out the state of the system either in the future, given the state of system now, or you want to know what it was in the past, you can work it out in the past. Okay? So that time reversal symmetry is already there, but there is no further consequence. Okay? But in quantum mechanics, discrete symmetries have consequences in the sense that they lead to certain properties of the system when there is an invariance under discrete symmetry. So I'll just mention, because I think my time is coming up. My left ear is completely gone because I did something and then I'm not able to hear. It's usually okay. I have to get it set right. So I'm sorry if I can't hear you very well sometimes. So the symmetries also can be continuous or discrete. Okay. discrete symmetries are relevant in quantum mechanics, and in particle physics we use it all the time. Okay. One such discrete symmetry is parity. Usually, now I am moving away from what I said in classical mechanics, because Noether theorem originated in classical mechanics, and then it is valid across board in quantum mechanics also. So, that is why I chose that example. But now back to quantum mechanics, parity is a discrete symmetry which takes, let us say, a vector r to minus r and momentum p to minus. It is like inverting the coordinate system. Okay. It is a discrete symmetry. There is no continuous transformation which takes you from r to minus r, except in 2 dimensions. I am talking about 3 dimensions here. In 2 dimensions, this is very special. You can take a vector in a plane and then rotate it by pi. Then from one quadrant you go to the opposite quadrant, where both x and y go to minus x, minus y. That is not a parity transformation, it is a rotation. So, in 2 dimension a parity transformation is where x goes to minus x, y goes to y, or y goes to minus y and x goes to x. If you write it in the matrix form, it has a determinant minus 1. So, we will come back to this question later when we talk about rotation groups. Okay. For now, in quantum mechanics, I will tell you what happens when there is, this is a discrete symmetry, this is a discrete transformation. I haven't said symmetry, I haven't said what the symmetry is yet, I will tell you. So, if parity operator P dagger or P, if I define this as the operator, then it takes this to minus r. I can define this as an operator relation. Now, if you operate it twice, it should come back to r. If you do it again, minus r goes to plus r. So, therefore, the property of this parity is that p square is equal to 1. It is Hermitian, therefore, p dagger p is equal to 1. But p squared is equal to 1, it means p dagger then is the same as p inverse. Okay. So, this is the property of the parity transformation. How does it affect our results? Let us look at the Schrodinger equation. For simplicity, I will use the one-dimensional Schrodinger equation, which is the stationary Schrodinger equation. Okay. So, now if I make a parity transformation on this, P operating on this, then this will go to x going to minus x is the parity transformation in one dimension. So, this is minus h cross squared by 2m. This is second derivative, therefore, it is unaffected, plus v of minus x under the parity transformation minus x. Okay. Of course, the two equations are different because this is V of x and this is V of minus x. But suppose V of x is equal to V of minus x. Can you think of any example where the potential is invariant under parity? Harmonic oscillator. You see, it's a parabola. X going to minus x, nothing changes, right? So it is invariant under parity, the potential. Therefore, the Hamiltonian of a one-dimensional harmonic oscillator is also invariant under this parity transformation. What it means is that if these two are equal, then the Hamiltonian is invariant under parity, and therefore psi of x and psi of minus x are both solutions with energy. They are solutions of the same equation. Okay. And since P of x is P on psi of x takes it to psi of minus x, and repeated operation, this is the same as P psi of minus x is equal to psi of x. But this is nothing but P square equals 1. So therefore, the eigenvalues of the operator P, since P squared is equal to 1, P of psi of x plus or minus 1. Eigenvalues are plus or minus 1, which means the following, that both psi of x and psi of minus x are solutions. Psi of x under parity operation goes to psi of x is one possibility because the eigenvalues are plus or minus 1, and psi of x under parity goes to minus psi of x. So the ones which change sign under the parity operation are called odd parity states, and these are called the even parity states. So if the Hamiltonian is invariant under parity, the eigenstates of the Hamiltonian have definite parity, which is either odd or even. They are eigenstates of the parity operator. Since they are invariant under parity, then P commutes, the operator P commutes with H. This we saw earlier. And that correspondingly, the states of the Hamiltonian carry definite parity, either odd or even. So if you remember your harmonic oscillator, what is the ground state? E to the power minus constant times x squared, apart from normalization. It's a Gaussian. So x going to minus x, what happens? E to the power minus x squared, remember, Gaussian. It remains the same. So the ground state of a one-dimensional harmonic oscillator carries even parity. It's an even parity eigenstate. It's an energy eigenstate, but simultaneously it is a parity eigenstate with even parity. Okay? So commuting observables have simultaneous eigenstates. Yeah. Yeah. No. Psi of x equals minus, and this is minus psi of minus x. Thank you. Thank you very much. Yeah. Okay. So then you take the first excitation of the harmonic oscillator. What is it? Very simple. Come on, this is the first problem you do. Ground state is a Gaussian, e to the power minus some constant times x squared. That constant depends on the oscillator constant, spring constant. That's it. What about the first excited state? Suppose you use this result, what should it be? You can make a guess. You don't need to solve it. What should be its form? Sorry? X times Gaussian, because it should be odd. It's a parity eigenstate. So it's x times Gaussian. If you go to second excited state, it is x squared minus a constant, some constants floating around, times the Gaussian, and then the next one, the leading term will be x cubed. And what are these polynomials? They are the Hermite polynomials. Hermite polynomials have even and odd parity. That's all. Hermite equation, therefore, is parity invariant. And that's what you have in one-dimensional harmonic oscillator. Okay. I think time is over. Okay. So one more thing I wanted to discuss was time reversal invariance, like parity, which is also a discrete symmetry. That also you can see what happens to the Schrodinger equation. It is different from parity in the sense that it will work only if you also simultaneously complex conjugate the equation. Then it becomes time reversal invariant. And then there is another discrete symmetry, which is a relational symmetry that you would have heard about, which is permutation symmetry. Okay? It's not a property of a single particle, but suppose you have two particles. Okay? Depending on the nature of the particle, it is either the wave function is either symmetric in this two particle wave function or anti-symmetric. What are they? Bosons and fermions. This is what you have heard. The wave function of a many fermion wave function is anti-symmetric under the exchange of any two of them. Any two of them you interchange, it gets a negative sign. Okay? This is an example of a discrete symmetry. Of course, we cannot show this discrete symmetry as the invariance, as coming from the invariance of some Lagrangian or something. It's an intrinsic property of all elementary particles and even composites. Either they are bosons or fermions. Of course, you also come to hear of other types like anyons and all. Those appear as quasi-particles, excitations of systems of many particles, which are essentially made up of bosons and fermions. So when you take an asymptotically free particle, it's either a boson or a fermion. These other types occur only in interactions. Okay? That's another example of a discrete symmetry. So therefore the symmetries can be continuous, and such symmetries of Lagrangian continuous symmetries are governed by Noether's theorem. They lead to conserved quantities. But in addition, in quantum mechanics, and later you will see in quantum field theory, that discrete symmetries also play a role. And in fact, there is one more which I could talk about, which is charge conjugation, but that takes me out of this essential framework that I am talking about. And there, the combination of charge conjugation, parity, and time reversal acting simultaneously on a state leads to what a very fundamental theorem called as the CPT theorem. That those who want to do go into particle physics study this CPT theorem. It's a very fundamental, it's a foundational principle theorem for elementary particles. Okay? So I leave it at that. You can read about these things.
Made the Lagrangian invariant under position and time, we got the subsequent conserved momentum and some
Continuous,
cases
continuous.
So can we make it invariant under x dot as well? We made it t and x. We made it invariant under t and x. From the Euler-Lagrange equation, can we make it invariant under x dot, and can we get some conserved quantity?
Well, in mechanics, if you make it independent of x dot, it is just a function of x, right? So, in terms of dynamics, that's not very interesting. Because what is it that you want to translate? Your fundamental space variables are x and t. There is one more, which is rotation. I didn't do that. If you do that, then you will get angular momentum. The rotational invariance, we'll do that actually. That I have postponed it. We'll do that.
Okay, thanks. We can defer the questions to the lunch session because lunch is waiting for us and they also need to leave after lunch, the people who are serving us. So let's go for lunch. Let's thank Professor Murthy and go for lunch.